नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर आईटी जेई एंड नीट. This is our problem series for JEE Advanced. We are going to discuss the theory through problems. Hope this will be useful for all of you. I will request you to like and subscribe our channel. So section 1, only one option correct type. This section contains 6 multiple choice question. Each question has 4 choices A, B, C, D, out of which only one is correct. This is the marking scheme plus 3 and minus 1. So the first question is the temperature of a definite amount of an ideal monoatomic gas becomes 4 times in a reversible process for which heat exchange is 0. Which of the following is correct relation between the final and initial parameters of the gas? So in this, the system is an ideal gas and this gas is participating in reversible adiabatic process. So we can write here, system is ideal gas participating in reversible adiabatic process. So before solving this problem, I want to revise some concepts of adiabatic process for an ideal gas. So the first point is, for an ideal gas participating in adiabatic reversible process, PV to the power gamma is constant, TV to the power gamma minus 1 is constant, and P1 minus gamma T gamma is constant. So these equations is valid only for adiabatic reversible. They are not valid for adiabatic irreversible process. Work done in adiabatic process, since Q is 0, we can write W is equal to delta U, and delta U can be written as HCV delta T. And this delta T and CV can be written in the form of R upon gamma minus 1. And this P2V2 minus delta T is equal to P2V2 minus P1V1 upon NR. So N will cancel out, R will cancel out. We can write that the work done in adiabatic process is equal to NR delta T gamma minus 1. The molar heat capacity of an ideal gas participating in adiabatic reversible process is equal to 0 because we are writing Q0, and Q is equal to NCm into delta T. We'll study that. In adiabatic expansion, delta T will be negative. In adiabatic compression, delta T will be positive. So delta T is non-zero. So Q will be 0 when molar heat capacity will be 0. For an ideal gas participating in adiabatic reversible process, there is no change in entropy of the gas. ds of the gas is equal to 0 because ds is dq reversible upon T. dq reversible is 0. So entropy change of ideal gas will be 0. Entropy change of surrounding will be 0. And there is no entropy change of universe. Universe is entropy change of system plus surrounding. So because of that, this ideal gas participating in adiabatic reversible process is known as isoentropic process. This is not only valid for ideal gas. Any substance participating in adiabatic reversible process, there is no change in entropy of system, surrounding, and universe. Therefore, that is isoentropic process. For an ideal gas participating in adiabatic irreversible process, these formulas are not valid. And molar heat capacity definitely will be equal to 0. And delta S surrounding is always 0 in adiabatic process because delta S surrounding is always Q surrounding upon T. In adiabatic process, Q surrounding is 0. That's why delta S surrounding is 0. But the entropy of system is going to increase in adiabatic irreversible process. Either the process is expansion or compression. If it is adiabatic irreversible expansion or adiabatic irreversible compression, the entropy of system is going to increase. And from there, I can write that the entropy change of universe will be positive. The work done in adiabatic process, I can write the same formula. While deriving the formula, there is no use of PV to the power gamma constant. So this formula is valid for adiabatic reversible as well as adiabatic irreversible. Free expansion of an ideal gas is adiabatic irreversible as well as isothermal irreversible process. In adiabatic expansion, temperature of ideal gas will decrease, and in adiabatic compression, temperature of ideal gas will increase. So now we are coming back to this question. The process is adiabatic reversible. Now I can use this formula in adiabatic reversible process for an ideal gas. I can write the final temperature upon initial temperature they have given. They have given that the temperature of definite amount of ideal monoatomic gas becomes 4 times in a reversible process. So T final is equal to 4 times of T initial. Temperature is increasing. That is possible when the process will be compression. So this process is adiabatic compression, adiabatic reversible compression we are discussing over here. So when we compress the gas, the pressure will increase and the volume is going to decrease. So if I write that, what is the relation? So by using those equations, suppose if I have to write about volume, I should write that T final, V final to the power gamma minus 1 is equal to T initial, V initial to the power gamma minus 1. Since it is a monoatomic gas, for monoatomic gas, we can write that the value of gamma is equal to 5 by 3. So now if I put the value here, we can write here that T final upon T initial is equal to 4. So in place of T final upon T initial, I can write this as 4. And here on the right hand side, I can write that V initial upon V final to the power gamma minus 1. Gamma is 5 by 3. 5 by 3 minus 1 is 2 by 3. So from here, if I calculate that what is the relation, so I can write that V initial upon V final is equal to 4 to the power 3 by 2, which on simplification is equal to 8. So we can say that V initial is 8 times of V final. Since we are compressing the gas, so the final volume is less than initial volume. So A option, we can say that A option is wrong and C option is also wrong. It is not satisfying the condition. What it is coming is V initial is equal to 8 times of V final. Now we can derive a relation for pressure. So for pressure, we can again write that T to the power 1 minus gamma, T to the power gamma is constant. If you don't remember, you can derive from the formula PV to the power gamma is constant. In place of volume, you can put temperature upon pressure. NR is constant, that you can take right hand side. So that will become temperature to the power gamma and pressure to the power 1 minus gamma. So P initial, T initial, and here it will be P final, T final to the power gamma. So now if I put the value over here, I can write that T final upon T initial to the power gamma is equal to P initial upon P final to the power 1 minus gamma. So from here, if I simplify, I can write that P initial upon P final is equal to T final upon T initial to the power gamma upon 1 minus gamma, and the value of gamma is 5 by 3. So if I put the value over here, T final upon T initial, we know that is equal to 4. So 4 to the power 5 by 3, and this is 1 minus 5 by 3. So on simplification, we are writing that this is 4 to the power, this 3 and 3 will cancel out. So this is minus 5 by 2. So on further simplification, I can write that this value P initial upon P final. On simplification, I can write that this is equal to 1 by 4 to the power 5 by 2. And on further simplification, I can write that this is equal to 1 by 32. So from here, we can write that the final pressure is equal to 32 times of the initial pressure. Final pressure is 32 times of initial pressure, means B option is correct. It means that D option is wrong. So answer for question number 1 is B. Question number 2, for 1 mole substance, variation of absolute entropy with temperature is given by the following graph. What is the molar enthalpy of vaporization? So this is the graph. It is starting from 0 Kelvin and moving to 100 and more, right? So at 0 Kelvin, a substance will exist in solid state. So this is related to heating of solid. Then there is melting over here. Solid is converted into liquid state when the temperature will be constant. And then this is heating of liquid. So here vaporization of liquid will take place. During vaporization, temperature is not going to change. And then this is related to heating of gas. So this graph is related to heating of solid. then conversion of solid to liquid, then heating of liquid, then conversion of liquid to gas, and then heating of gas. So first we revise the concept regarding entropy change during phase transition. Entropy change during melting, we can say that A in solid state is in equilibrium with A in liquid state. When melting is taking place at melting temperature and pressure, there is an equilibrium between solid and liquid state. So here, this line at any point on this graph is related to melting point, and there is an equilibrium between solid and liquid state. At that point, delta G is equal to 0, and we can write that delta G is delta H minus T delta S. Since we are talking about melting, melting is also known as fusion. So we can say that delta H fusion minus T delta S fusion is equal to 0, or delta S fusion, entropy change during fusion, is delta H fusion divided by fusion temperature or melting temperature in Kelvin. Same way I can write that entropy change during vaporization. So when vaporization or boiling is taking place at its boiling point, we can say that delta G is equal to 0, or delta H minus T delta S is equal to 0. And from there, we can say that entropy change on vaporization is equal to delta H vaporization divided by temperature. And entropy change during sublimation, in the same way, we can say that for this graph, this is sublimation graph, right? So here solid to gas conversion. So on this graph, there is an equilibrium between solid and gas. So we can say delta G is equal to 0. And from there, we can say that entropy change on sublimation is equal to enthalpy change on sublimation divided by the sublimation temperature. This point is a triple point. There is an equilibrium between solid, liquid, liquid gas, and solid and gas. And for all this equilibrium at triple point, the pressure and temperature will be same. So that is different from the other cases of melting, vaporization, and sublimation. The temperature is different, but at triple point, the temperature is same for all the processes. So when we discuss a triple point, there is an equilibrium between solid, liquid, and gas. Therefore, I can say that since temperature is same, I can write that delta S sublimation is equal to delta S fusion plus delta S vaporization. Delta H sublimation is equal to delta H fusion plus delta H vaporization. The vapor pressure of solid form of the substance is equal to the vapor pressure of the liquid form of the substance. I can't write this or this at any temperature. That is valid only at triple point, where there is an equilibrium between solid, liquid, liquid gas, and solid and gas at the same temperature. And because of this same temperature, we are able to write all these things. So this is important. We are using in numerical. And the important point is that when melting is taking place at melting point, or boiling is taking place at boiling point, or sublimation is taking place at sublimation point, temperature remains constant. Temperature is not going to change. So now let us solve this question. They are asking about enthalpy of vaporization. So we can say here that this is solid, then here liquid will be there. And then this is heating of liquid, and here vaporization of liquid is going to take place. So I can write that vaporization is taking place at boiling point. We should write here that delta G is equal to 0, and delta G is equal to delta H minus T delta S. So I can write that delta S vaporization is equal to delta H vaporization divided by vaporization temperature or boiling temperature. And from here, I can write that delta H vaporization is equal to T delta S vaporization. So temperature is constant, that is equal to 100 Kelvin. And the entropy change here from 400 to 600, entropy increased by 200 units, right? So here we can write that this is Joule per Kelvin. So from here, we can find out that what is enthalpy of vaporization. This answer is in Joule. So if I have to convert into kilojoule, we'll divide by 1000. So this is 20 kilojoule per mole. So enthalpy of vaporization, from here I can calculate. Same way, by this difference, I can calculate that what is the enthalpy change of, this is solid to liquid, so fusion, delta H fusion. If I have to calculate delta H fusion, I can say that that is equal to 50 into entropy change, that is equal to 100. So this value is equal to 5 kilojoule per mole. So delta H fusion is 5 kilojoule per mole and delta H vaporization is equal to 20 kilojoule per mole. So the answer of this question will be C,